Welcome to the HFSS version 9 Quick Start Antenna Demo. Here, we will show you how to analyze an antenna using HFSS, including a discussion of setup and post-processing. Now it is hoped that you have already worked through the Getting Started problem and know a little bit about the interface. We are going to analyze a simple, unflanged, rectangular waveguide operating at 10 GHz. It will be easy to set up and quick to solve. Now for the purposes of this simulation, we will ignore the thickness of the walls of the waveguide and will also ignore the conductor loss. Now I have already drawn in the waveguide and set the drawing units to inches. The bottom face is centered about the origin with a cross section that is 0.4 inches high in the Y direction, 0.9 inches wide in X, and since we want to space the port a distance from the aperture, we've chosen the length of the guide to be 0.5 inches in Z. Now if this is your first time solving an antenna in HFSS, you need to realize that HFSS is solving for the electric field in and around the device. So we need to put an air box around the device that will have an absorbing boundary condition, or ABC, defined on its faces. HFSS will solve for the fields in the guide and in this air box. It will then integrate the results over the ABC to compute the radiated fields. Now it is recommended that the ABC boundary in HFSS be placed at least a quarter of a wavelength from the radiating structure. In this case, we will solve at 10 GHz, where the wavelength is 1.18 inches. So a quarter of a wavelength is roughly 0.3 inches. We will draw an air box that is 0.3 inches wider on the sides and on the top. Now we will define the bottom of the guide to be the port, and so the air box and the guide will lie in the same plane on that face. So let's click on the Draw Box icon and just sketch the box in our window. We will edit the parameters in the Properties window. First position is -0.75, -0.50. Using the arrow key, we input an X size of 1.5, 1 for a Y size, and 0.8 for Z. We click on Attribute, and let's change the name to Airbox. We will accept the default material setting of Vacuum, but let's change the color and the transparency. We click OK, and the model is complete. Next, we need to define the ports and boundaries. We need to go to Face Select mode. And first, let's define the walls of the waveguide. So we need to use the B key, which is the next behind key, and the multiple select key, which is Control, to select the four sides of the waveguide object. Once we've done that, we right mouse click in the window and go to Assign Boundary, Perfect E, and we can accept the default name. We will then notice under the Boundaries folder that our Perfect E boundary is defined. We next want to define the radiation boundary. We want to do this on all sides of the air box. To select those faces, click on one face on the air box and right mouse click and go to All Object Faces. And that will select all of the faces on the given object. Right mouse click again, go to Assign Boundary. The name for our ABC is Radiation, and again we accept the default name and see that boundary definition listed in our Boundaries folder. Our boundaries are now defined. Last step, we need to define the port. Again, using the B key, we select the correct face. We right mouse click and go to Assign Excitation, Wave Port. Again, we'll accept the default name. Now one mode should be sufficient for this device, and we are not concerned about an integration line. So we click Next, and again for this simulation we don't need to worry about renormalizing or de-embedding, so we click Finish, and our port definition is complete. But I want to point one thing out. If you'll notice in the message window, there's a warning regarding a boundary overlap. The port overlaps part of the radiation boundary on the bottom face. Ports take precedence over other boundary conditions, and that is what we want. Therefore, we are not concerned about this warning. Now, as with all problem setups, we recommend that you check your boundary definitions. Go to HFSS, Boundary Display, and it takes the solver a second or two to compute the boundaries. We will then be able to view the boundaries in our 3D window. We click on Perfect E. We see our waveguide. Radiation should cover all faces of the outer box except for that face that the port's defined on. We see that to be true. Then our port is on the bottom. So it looks like our port and boundary definition is correct. For the last step, we assign the solution setup. That's a right mouse click on Analysis, Add Solution Setup. We want to solve at 10 gigahertz. Let's set the maximum number of passes to 8 and set our delta S to 0.01. And click OK. Now the solution setup is complete. Let's take a quick look at how we seed the mesh. Seeding a mesh gives instructions to the solver to add extra tets to the given object. In this case, we usually recommend that you seed the radiation boundaries. HFSS computes the radiation fields by integrating over the faces of the radiation boundary. So the finer the mesh on those faces, the more accurate this calculation. To seed the mesh on the faces of our airbox, we go back to Object Select mode and select the airbox object. We then right mouse click, go to Assign Mesh Operation, on selection, that means we want to do it on the faces, and go to Length Based. Here we can give it mesh instructions with regard to the maximum size of a tet length or how many tets we wish to add. Now we typically recommend that you seed to a tet length of roughly lambda over 6 when seeding in ABC. In our case, that's 0.2 inches. So let's enter 0.2 for the length of elements and click OK. And we will see a mesh operation added. Now lastly, we always double check our setup by clicking on the validation icon. HFSS tells us that everything is correct, but again points out the boundary warning. So we are ready to solve. We right mouse click on the setup that we inserted and go to Analyze. Now we pause the video during solve. The solution is now complete. We can right mouse click on our setup and go to Matrix Data, where we can see that S11 for the last adaptive pass is roughly 0.33. Now to view the fields inside the solution region, you can create a 2D shade plot or 3D volume plot using the same procedures as described in the Getting Started guide. Now rather than repeat those steps, let's instead look at the antenna-specific post-processing features. Let's create a radiation pattern. To do that, you first must create a pattern definition. You do that under the Radiation folder. Right mouse click, Insert Far Field Setup, Infinite Sphere. Here is where you will define the desired pattern cuts. Now we will first create a 3D polar plot, and for 3D patterns you will want many phi cuts. But for the purposes of this demo, let's increase the phi step size to every 30 degrees, and we will decrease the theta step size to every 2 degrees. Now if we had defined a new coordinate system, maybe in the aperture plane, we could change the coordinate system that the software uses when computing the radiated fields here in this tab. Also, if we had defined a custom radiation surface, the surface that the solver integrates over when computing the radiation patterns, we could select that under this tab. Now we haven't discussed PMLs yet. A PML is a perfectly matched layer, and it can be used instead of a radiation boundary. If we had used one, we would need to define a custom radiation surface and set it under this tab. Now for more information on PMLs, please check out the online help. We click OK and see that we now have one pattern definition in our radiation folder. Now to create patterns, we call up the same Traces dialog box as used for S-parameter plots. So we right mouse click on Results and go to Create Report. Unlike S-parameter plots though, we want to change our report type to Far Fields. For display type, let's first choose 3D Polar Plot. We can click OK. Now note, since we are doing a 3D polar plot, there are two angle tabs and the magnitude tab. We can see under the Theta tab that Use Secondary Sweep is selected. Under the Phi tab, we can see that Use Primary Sweep is selected. Checking the Sweeps tab, we can see that the primary sweep is Phi and the secondary sweep is Theta. Now for 3D polar plots, we typically do not need to edit the default settings for these three tabs. So let's go back to the Magnitude tab. I want to point out that if we had more than one pattern definition, we could select which one to use here in the geometry box. Let's look at some of the antenna-specific quantities that are available. We have directivity, which is normalized to the radiated power, gain, which uses the accepted power, and realized gain, which uses the input power. Let's choose the gain. We will plot the total gain, and for function we will plot it in dB. We click on Add Trace to add the trace to our plot, and then click Done. Now we'll take the solver a few seconds to compute our 3D polar plot of the gain for this waveguide antenna. And here it is. Now we can rotate this using the Alt key, and holding down Shift Alt we can zoom in. Let's close this plot, and let's now generate the E and H plane patterns for this antenna. Note from the model that at phi equal to 0 should be the H plane, and that for phi equal to 90 should be the E plane. So again, we go back to Results, Create Report. We're going to again select Far Fields, except this time now, for display type, let's choose Radiation Pattern, and click OK. Notice we're only doing a 2D polar plot, so there's only one angle tab. And under the Angle tab, we see that by default, Use Primary Sweep is selected. Now we do need to go to the Sweeps tab because we see that our primary sweep is still Phi. Now we want to plot versus Theta, so we need to change our primary sweep. To do so, click on the name Phi and choose instead Theta. Phi now becomes our secondary sweep. Now for 2D patterns such as this, the values of the secondary sweep will correspond to additional curves in our plot. Now we do not want to plot all of the Phi values. We only want 0 and 90 degrees. So we select Phi, turn off all values, and holding down the Control key, select the two Phi values, 0 and 90, that we wish to view. We go back to the Magnitude tab, and again, let's choose Gain, Total Gain, dB, and we add the trace and click Done. And here is our E and H plane patterns for our antenna. We can right mouse click here and zoom in to see the forward direction. If we wish to compute 3 dB beam widths, we also provide data markers that you can add to your plot. But let's close this plot. Those are the main antenna post-processing features. You can also plot the near-field solution if you desire. To do that, go to Radiation, Insert Near-Field Setup. If you choose this option, you would get a similar dialog box to the one that we got before for the far field setup, except you would also be defining a radius. If you had defined a polyline that you wish to view the fields on, you could choose this option and have the software compute the near fields along that line. Once you had inserted that, you could go back to Create Report, and under Report Type you would select Near Fields. Also, if you want to just view the maximum values for gain and directivity, and also to look at radiated power, you can right mouse click on a given far field setup and go to Compute Antenna Parameters, and the software will compute those values for you and present them in a simple table. Now there was much that we could not show in this short time, so please take a few minutes to look at all of the post-processing features that are available to you in HFSS. That then concludes this demo.